All right, very good.
Yeah, I hear you.
All right, thank you. Okay, so I'll go ahead and just get started. Let me just kind of briefly introduce myself first. So my name is Elliot, and I will be leading the first 2 days, so today and tomorrow, of the Calculus Workshop series. I'm going to be just kind of going over some things that you should have covered in pre-calculus. And then starting on Wednesday, Thursday, and Friday, my colleague Leszek over here, he goes by Les for short, he will be kind of introducing you to like the first couple of topics that you'll encounter in calculus. So that's what the kind of a overview of the week is going to be. Okay. If you guys have any questions at any time, you can post them in the chat. I will try to respond to them if I see them. If I don't see them, my colleague is also here to respond to them as well. So he'll be monitoring the chat for me. Yeah. So for today, I'm going to start by looking at some examples of algebraic functions. And we're just going to kind of look at some of the aspects or characteristics of them and some examples. And I'll just try to highlight the things that I want to highlight in the examples. Okay. First, I thought it would be useful to just give a definition of an algebraic function. This is a definition that I kind of just came up with by myself, so it's not like a definition I found in a book or anything. But basically, an algebraic function is a function that involves only powers of x, and then the operations of addition, subtraction, multiplication, division, and raising to a power. So just kind of some examples of algebraic functions right now. So probably the simplest ones are the polynomials. Yep. So these would be functions like f of x equals, I don't know, x cubed minus 2x squared plus 5, something like that. Other examples of algebraic functions, so something a little bit more complicated than polynomials are what we call rational functions. So a rational function is just whenever you have a polynomial over another polynomial. Okay. So an example of a rational function, if I just make one up on the spot here, so it's a polynomial over another polynomial. Okay, so that's an example of a rational function. So it's an algebraic function because again, it involves like basically, just powers of x, and then it also has division going on between them. Just a few more really quick examples. In the definition, there's no restriction that the powers have to be whole numbers. So we could have, say, x to a power of 1/2, which of course, I think you guys know can be rewritten as the square root of x. So that's also an algebraic function. And then you could have kind of a mixture of all these things. So something like square root of x squared plus 1 over x squared minus x. So that would, all of these here are examples of algebraic functions, okay? And I'm going to spend the first part of today looking at examples of algebraic functions, and I'll just be highlighting some of the characteristics of each of those examples. All right. And I want to start with, I guess, a kind of a simple function. So I want to start by looking at this function f of x equals 1 over x. Could someone maybe tell me what the domain of this function is? Yeah, what's the domain of this function 1 over x? All real numbers but 0. Okay. So yeah, let's talk about the domain right now. So as a sort of a refresher, what was the domain of a function? So domain of a function is defined to be the set of all x values, for which the function is defined. And when you look at this function here, 1 over x, one of the things that is undefined in mathematics is division by 0. Okay. Okay. So that means you cannot plug in 0 for x into this function. That would sort of break mathematics, if you will, if you try to do that. So the domain of this function, a couple people have gotten it right in the chat. It's going to be all real numbers except 0. Okay. And x equals 0, we have to exclude it because you would be dividing by 0 when x is 0. Okay. Now, some people have also answered the question using interval notation. Okay. So to express all real numbers except 0, that would include everything from minus infinity up to 0. But if I want to exclude 0, I would use open parentheses to indicate that I'm excluding 0 from the interval. And then we also have everything from 0 to infinity as well. And we have this union symbol to indicate that the domain is both of those intervals, not just one of them. Okay.
Oh, so like the parentheses, that it excludes the number, right?
That's right. Yeah. So like as an example, if you have like the interval 1, 3, just sort of it as an aside. So that interval will include both the endpoints 1 and 3. But if you have the parentheses on one of the endpoints, that means it's excluded. So this interval includes 1, but this one will exclude 3. Okay.
I think after 2 or 3 years, that's the most simplest explanation that someone's given me about that.
All right. Yeah. Oh, and then I know sometimes it's a little bit confusing because, if I write something like this down, you might be wondering, is this referring to an interval? Or is it referring to like an ordered pair, right? So I know sometimes that can be confusing as well. So I guess for that, you just have to kind of judge based off the context. So if someone writes something like that down, maybe based off the context of what they're talking about, you can figure out if they're referring to the interval 1, 3 or the ordered pair 1, 3, right? So yeah, I know I've seen students get confused on that before as well. All right, so going back to this example with the function 1 over x. So you guys have correctly identified that 0 is not in the domain. Maybe if I were to ask you like graphically, what's going on at x equals 0? Does anyone know?
There's an asymptote, yeah. All right.
Okay, yeah, there's an asymptote there. Okay. So if you were to look at a graph of this function, I'll just give it sort of a quick sketch of the graph. It looks something like this. But yeah, so specifically here at when x is 0, so that's the y-axis, your function has a vertical asymptote at this location. So I'll use the abbreviation VA for vertical asymptote. Okay. A Discord answer? I'm not imaginative enough to see that, but I'll take that as a compliment though. All right. All right, so maybe if I were to ask you guys, like, how do you know that there's a vertical asymptote at x equals 0? So what kind of gives it away? Or maybe like, what do you look for in a function to determine where the vertical asymptotes might be?
I think it's like, I think so you have to solve it first, right? That's how you ended up getting 0. You have to like set it to,
You set, so you're saying like set something equal
wait,
to 0, I think.
yeah, like something.
Oh, okay, very good. Okay, yeah. All right. Yeah, so I want to talk a little bit about vertical asymptotes. So vertical asymptotes, they tend to occur whenever your denominator becomes 0. Okay. I'll have more to say about this later, but for now, I'm just going to say that vertical asymptotes, they tend to occur when the denominator is 0. Okay. And as for an explanation for why that's the case, I saw someone in the chat give a pretty good explanation of that, actually. But let me try to explain it as well in my own words. So I'm just going to be using this function 1 over x to try to illustrate it. So we know that this function is not defined at x equals 0, but if we think about what's happening when x is close to 0, okay, so not equal to 0, but what happens when x is close to 0? So maybe what I'll do is maybe I'll like tabulate some values. So I'm going to choose some small values of x, which are not 0, but close to 0. So maybe I'll start with like 1/10, 100th, 1,000th, and so forth. So here I have some values of x which are really close to 0, okay, but not quite equal to 0.
I think that's where like limits would come in, right?
That's true, yeah, okay, good. So if you plug these values of x into our function, so if x is 1 over 10, f of x would be 10, so it's just 1 over x, so the reciprocal, yeah, and then so forth. So yeah, so what's happening is our function is kind of like blowing up, if you will, in value as x is approaching 0. And here I'm looking at x kind of approaching 0 from the right because I'm only looking at the positive values of x, at least in that table there. So like at 1/10, it's at a value of 10. But then when you go to like 100th, now it's at a value of like 100. And so you can kind of see how it works if you try to plug in some values which are getting closer to 0. Your function tends to shoot upwards in value as x is approaching 0 from the right. Yeah, that's right. Okay. Now, similarly, if you were to plug in some negative values of x, so what you find is that as you plug in negative values of x and they get closer to 0, your function also kind of blows up, but it's going to be negative as well. And that's how you kind of get this indication that you have these vertical asymptotes there, okay? So I'm not going to talk about limits too much, but I know someone already mentioned it earlier. So limits are kind of the first topic that you encounter in your calculus courses. And limits, I mean, if I were to give like a rough explanation of what limits are right now, limits involve this idea of getting like closer and closer to something, and then like what's happening as you get closer and approach something, okay? So my colleague is gonna get more into that in the latter half of this workshop series. For now, I'm just kind of dropping little like hints here and there of what he'll be doing and what you'll be doing in your calculus classes as well, okay? By the way, so everyone pointed out that we had this vertical asymptote at x equals 0. Do you guys notice that there's also a horizontal asymptote in this example as well? So yeah, if you look at this graph here, it also has a horizontal asymptote along the x-axis, which is where y is 0. Okay. And so I also just want to maybe briefly talk about, so how could you sort of figure out that there's a horizontal asymptote for this function? Now for the horizontal asymptote, what happens is your function is getting closer and closer to it as x goes further and further out. So you can maybe think like if you were to take values of x that are getting further and further away from the origin, and if we were to plug those into the function 1 over x, okay, so this function just takes the reciprocal of each of these x values. And so here you see that the function values are getting closer and closer to 0 as x goes further and further out. So in other words, getting closer and closer to the x-axis. And so that's kind of the indication that you end up having the vertical asymptote there. Okay. And so here, there's this notion of x kind of like approaching infinity, if you will, if you're going further and further out. So roughly speaking, it's like as x is approaching infinity, your function is approaching this value of 0. And that's kind of the indication of having a horizontal asymptote. Okay. Great. So that was just looking at this function 1 over x. So it seems like a pretty simple function, but already we're seeing some interesting things happening with vertical asymptotes and horizontal asymptotes. Okay. So I'm going to look at a little bit more complicated function now. So maybe let's do this first. Okay. So here I'm looking at another rational function. So it's a polynomial over a polynomial. We call those types of functions a rational function. So maybe if I ask for the domain of this function again. Okay, so you could tell me what the domain is, or maybe like how you would figure out what the domain is.
You'd
Okay,
have
all
to
right,
like
yeah.
factor it out first and then.
Okay, all right, yeah. So I see a lot of people kind of giving the right answer, but maybe specifically though, so again, we have this idea in mathematics that, you know, we can't divide by 0. Yeah, there you go. So you can't divide by 0. So what we want to do is anytime we have a function with a denominator like this, and we're looking for the domain, yeah, we want to check where the denominator might be equal to 0. Okay, so yeah, if I take the denominator x squared minus 4 and set it equal to 0, to sort of solve for x, I guess for this problem, you can do it a couple of different ways. So maybe first is, I know a lot of people have said you can factor it, right? So x squared minus 4 would factor as x minus 2. times x plus 2. And then from there, you get that the denominator will be 0 when x is plus or minus 2. Okay. Now, these are the places where the denominator is 0. That means these are the places that would not be in the domain. Okay, so the domain is going to be everywhere else except when x is plus or minus 2.
So whenever you find the square root of the number, the plus when it's plus or minus, that means that's the one it's not going to be equal to.
Right. Mm-hmm.
All right.
Yeah. So I guess that's kind of funny if you think about it, perhaps. But I guess the usual strategy for finding the domain of a function is actually to find where it's not defined, and then you're going to remove those points from the line, from the real line, to get the domain. So here's kind of like a visual representation of what the domain would be. So it's everything except x is plus or minus 2. So then if you were to write it in interval notation, I've seen a couple people do it already. So it's the interval from minus infinity to minus 2. So that would kind of take care of everything in this left part. You have the portion in the middle, so that's everything between -2 and 2. And then lastly, we have this portion on the right, which is everything from 2 to infinity. And I'm using sort of like parentheses rather than brackets for all of those because I want to exclude -2 and +2. And I guess from minus infinity to infinity, you'll always put parentheses on those two because we don't really consider them as part of the real line. Okay. Okay, so that's good. So for the domain, we checked where the denominator was 0. Is there anything special to the numerator being equal to 0? Okay, yeah. So where the numerator is 0, that will give you where the x-intercepts are, because that's where the function would be equal to 0. So yeah, if you wanted to find the x-intercepts of this function, x-intercepts are where your function is equal to 0. And when you set this function equal to 0, you can multiply the denominator to the other side to solve this equation. So in a sense, you really just look at where the numerator is 0. And then here we could factor this to try to solve for x. Who knows how to factor this polynomial?
You have to split it up into two different parts. You'd have to start off with the
Mm-hmm.
x, and then you'd
Okay.
have to, because since the last value is negative, one of the values has to be negative, and the middle variable, the negative x, it'd have to be like, it'd have to be like, it had to subtract, like the two values have to like subtract each other or something. So it'd have to be like x minus 4 times x plus 3.
Yeah. Okay. Yeah. All right. Good. Yeah. So you guys are going to be factoring a lot in your calculus classes. So definitely factoring is something that you want to be comfortable with, I would say. Okay. So yeah, for this problem, x-intercepts would be at x equals -3 and x equals +4. Okay. Okay. So if I were to maybe get like a rough sketch of what this function might look like, its graph. See, so when x is -3, I know that it has an x-intercept there. So it'll pass through that point. When x is positive 4, it also has an x-intercept there, so I know the graph would also pass through this point. We saw that -2 and +2, those are not in the domain. So this function will actually have vertical asymptotes at these locations. Okay. Now, maybe let me focus on the vertical asymptote here right now, where x is equal to -2. How can we determine if the graph is maybe like shooting upwards, or is it maybe like shooting downwards at this point here? Okay. So how would you guys maybe try to determine what the graph looks like at this vertical asymptote?
And you have to look at.
Yeah, okay, yeah. So a couple of people have been suggesting to just plug in some points, and so that's pretty much how I would be doing it as well. So we want to kind of imagine if we're plugging in a value of x that's close to -2, but a little bit to the left right now, okay? So here's the function again. And I guess when you're plugging in points to kind of test whether it should be, I guess, like positive or negative, I find that it helps to write your function in its like fully factored form. So here we saw the numerator factored as x minus 4, x plus 3. We saw over here when we were looking at the domain that the denominator factors as x minus 2, x plus 2. So yeah, so if we think about plugging in a number that's kind of to the left of -2, so here, if we just kind of think about what would the sign of each of these 4 factors be. So if x is to the left of -2, x minus 4 should be negative, right? Now, if it's to the left of -2, but assuming that's close to -2, though, like in this picture, x plus 3 will end up being positive then. X minus 2 looks like that would be negative. X plus 2, so here x is slightly to the left of -2, so if we add 2 to it, we're still going to be a little bit less than 0. So that would still be negative, it looks like. So based off this kind of sign analysis, it would appear that the function should be negative then, when x is less than -2, but close to it. So that kind of suggests to me that the function, its graph is probably going down then when you're approaching the vertical asymptote, x equals -2 from the left, okay? All right, so maybe you guys have any questions about like how I did that kind of analysis there? Yep, no problem, yeah. So the idea is to figure out what's going on to the left of this vertical asymptote. I imagine plugging in a value that's to the left of -2, but close to it. So you can maybe imagine something like, if I were to use like a specific number, something like -2.1. So it's close to the vertical asymptote, somewhere to the left. And you think about if you plug it into the function, I'm just trying to figure out whether it's going to be positive or negative. So I don't necessarily care too much about the exact value. So if you plug something like -2.1 to each of these four expressions, they end up having these signs. This would be negative if you plugged in something like negative 2.1. If you add 3 to it, it'll end up being positive. If you subtract 2, it'll be negative. If you add 2, it'll be close to 0, but it'll still be negative. And then the 3 negatives altogether indicate that's going to be approaching negative infinity.
I could be wrong, but
Yeah.
couldn't you determine that it would that part of the graph would be shooting downwards if you were just looking at the function itself because of all those like subtraction symbols? Because that's what I think. I could be completely
I see.
wrong, but like, could that work that way too, or?
I would say no. I don't think you want to draw that kind of conclusion, at least. So I like to think I could make another function that has lots of minus signs, but if we were to do this analysis, that it would have been like positive, for instance. So I like to think I could have done that.
All right.
So yeah, I wouldn't say that it ended up being negative just because of all the minus signs in the function. I don't see any reason why that would be the case.
Okay,
Okay,
thank you.
yeah, all right. Yeah, no problem, yeah. All right, so here I kind of wanted to introduce just kind of the idea with this example of how to determine if your function should be like approaching negative infinity or positive infinity around a vertical asymptote. The basic idea is to plug in a number that's close to the vertical asymptote and analyze what the sign of your function should be. Should it be negative or positive? Yeah, someone asked about the horizontal asymptote, so I also wanted to ask you guys about that as well. Looking at this example of this function here, does anyone know if it has any horizontal asymptotes, and if so, where? Okay. Yeah, so a couple of people have the right answer. So y equals 1. So let me try to give a little explanation of why you'd have a vertical asymptote at y equals 1. So some of you already know that that's the answer. But if I just want to talk a little bit about like maybe like why is that the case? How can we tell? Yeah, okay. So remember that the idea of a horizontal asymptote is if your function has a horizontal asymptote, it should be approaching that asymptote as x gets further and further out. Okay, yeah. Yeah, so if you guys are feeling rusty on that on this stuff, it's not necessarily bad. So we're reviewing right now, right? So it gives you an opportunity to maybe be a little bit less rusty. Yeah, all right. Yeah, so looking at the horizontal asymptote here at y equals 1. So the idea is that your function should be approaching this value as x goes further and further out. So if we think about what's happening to our function, if x is, say, like a really, really large number, and here I'm being maybe somewhat informal, so I'm just kind of imagining what happens if x is a really, really large number, okay? And here, I guess my intuition when I look at this at least is, well, I know when x is a large number, x squared is going to be much larger. If I square something big, I get a much bigger number. So when I'm looking at everything in the numerator and the denominator, the highest power is x squared, and my sense at least is that that term is going to sort of overpower all the other terms, which are smaller. So it's almost as if in the numerator, that minus x and minus 12 are almost kind of insignificant when x is large. So it's almost as if you just have x squared in the numerator. And kind of similar in the denominator, if x is large, that minus 4 looks pretty insignificant next to the x squared. So it's almost as if it's not there. So x squared over x squared simplifies to be 1. So it kind of looks like when x is large, your function should be close to 1. And that's kind of the idea of why it would have a horizontal asymptote at y equals 1 then. Okay? Okay, all right. So I'm talking a lot about vertical and horizontal asymptotes right now. I see. That's an interesting question. So maybe I'll address that in another example, okay? So if you had an asymptote of, say, like y equals x, that is possible. Sometimes we call that like a slant asymptote, right? Because it's not like horizontal or vertical. So we might call that a slant asymptote. Okay. But yeah, so with these first couple of examples, I've been pointing out like horizontal and vertical asymptotes a lot. So I guess to like give like a really formal definition of each of them, I guess like the formal like definition or characterization of these horizontal and vertical asymptotes involves limits. So when we get to the actual calculus portion of this workshop, we might revisit horizontal and vertical asymptotes, but in the context of limits to try to make them more precise. Okay. Now, so horizontal asymptotes, we kind of think about what's happening when x is a really large number. For the vertical asymptotes, we've kind of identified the vertical asymptotes by looking at where the denominator is 0, is what we've been doing. So I guess I wanted to ask everyone another question now, which is it always the case that if your denominator is 0, you're going to have a vertical asymptote?
I want to say no.
All right. Does anyone disagree with that? Okay, yeah, all right, good. Yeah, so I do want to highlight this fact, which is just because the denominator is 0, it does not necessarily mean that your function has a vertical asymptote there, okay? So just kind of a simple example of that. Would be this function x squared over x, okay? So if we look at this function, it seems kind of strange, I guess, because probably what you guys are immediately thinking right now is, can't we just cancel out an x from the numerator and denominator? So yes, we could. So we cancel out 1x from denominator and numerator. We see that this function is really just equal to x, except for the case where x is equal to 0. Because if you look at the definition of our function, if you try to plug in 0 for x, you're actually going to be dividing by 0, which is no good. So this function x squared over x, its domain is all real numbers except x equals 0. And if I were to draw kind of a graph of this function, yeah, so good question. So it is true even after we simplify it to x, because this simplification that I did here, that's only good for values of x which are not equal to 0. But it's still the case that when x equals 0, you would be dividing by 0. So in that sense, 0 is still not in the domain because of that. Okay. Yeah. Okay. Yeah. So when you look at the graph of this function, it basically looks like the line y equals x. Except at x equals 0, there's actually a hole there when x is equal to 0. Okay. In particular, though, so we have a hole and not a vertical asymptote, right? Yeah. Okay. Yeah, so this does get into discontinuities a bit. So again, we'll talk more about discontinuities when we get to like the actual calculus stuff. Yeah. All right. Right now, what I'll maybe say is this though. So to sort of answer the original question. So just as a sort of rough statement right now, if it appears that the 0 in the denominator cancels out, then you're not going to have a vertical asymptote, but rather you'll have something like a hole instead. Okay. Yeah, no problem. So I'm always happy to answer all the questions that you guys have. So please feel free to ask them whenever you have them. So then I guess I would say that for both like the hole and the vertical asymptote, so both of them do occur when the function is undefined, at least in the examples that we've seen here. And I guess what sort of distinguishes them is when you have a hole, it kind of looks like the 0 can be canceled out. Whereas for a vertical asymptote, so going back to the 1 over x example, for vertical asymptotes, the 0 in the denominator does not appear that it can sort of cancel, if you will. Okay. So that's kind of the difference between like the hole versus the vertical asymptote. The vertical asymptote, there's a 0 in the denominator, but like not in the numerator, you could say. For a hole, you have zeros in both the numerator and denominator. And if we sort of push aside the issue that we can't divide by 0, then it kind of looks like you can cancel the 0 out. So it's kind of like there's like not that much of an issue because of that. So you don't have an asymptote, but you do have a hole instead. Okay, all right. Yeah, so how do I know if I have a slant asymptote? Yeah, let me go ahead and address that question right now. Yeah, all right. So I guess this is a small aside about slant asymptotes. All right. I guess maybe I'll create an example to maybe illustrate when it might happen. I don't have an example prepared, but I will just make one up on the spot right now. Okay, so here I just made up a function. Maybe a quick question is, you guys understand how I simplified this into this common denominator? I see. Okay, yeah, all right. So yeah, someone did notice that in this example that I created here, which has a slant asymptote, the numerator has like a power 1 higher than the denominator, or the degree of the numerator is 1 higher than the degree of the denominator. So yes, that tends to be the case whenever you have a slant asymptote. But then maybe if you have a question like, what is the equation of the slant asymptote, right? So that's not something that you could determine, I think, just by noticing the difference of 1 in the degrees. So I think usually for finding a slant asymptote, you'd want to do like a sort of polynomial division. Whether you do polynomial long division or I think some of you might know like the sort of synthetic division, if they still teach that. It's been like many years since I learned that stuff, so I don't know if they still talk about it. But here, but I don't want to get too much into. Yeah, okay. All right, so you guys are kind of like me. You don't remember it too well. But I don't want to go on a little polynomial division aside right now, though. But what I will say about this example is, so I set it up as to where it was equal to this, and then went ahead and just simplified it to be that. But if we look at this particular expression of our function, and if you think about what's happening as x gets larger and larger, okay, so in particular, this 1 over x squared plus 1 term, if x is really big, you have 1 divided by a really big number, that's going to be a really small number, right? So this 1 over x squared plus 1 term is going to get closer and closer to 0 as x gets larger and larger. And so therefore, our function is going to get closer and closer to being just equal to x because that second term here gets smaller and smaller, okay? So when you look at the graph, I don't know exactly what it looks like, but because we see how it gets closer to this line as x gets larger and larger, that kind of indicates in the graph that at some point, its graph might be doing maybe something like this. And you had like that slant asymptote there all of a sudden where y is equal to x. Okay. So that's kind of the idea of why would you have a slant asymptote in this kind of situation, okay? All right. All right, cool. So let's see here. All right, let's look at a quick example, one more of this type. So I'm going to look at least for now, one more example of a rational function. Okay, all right. Well, this example has a horizontal asymptote, so let's address that question with this example, okay? Yeah, so for this function, we're just going to kind of look at the same things that we've been looking at so far. If you guys could maybe work it out and tell me what's the domain of this function, where would the vertical asymptotes of this function be? Maybe where would the holes be as well, if there are any holes and or vertical asymptotes. And then we'll also talk about the horizontal asymptote as well, okay? Okay. So about the domain of this function first, you can tell me what the domain is and how did you figure that out? Yeah, okay, yeah, that's right. So for domain, we will look at where the denominator is equal to 0. Okay. And yeah, here we might factor it to solve for x. Okay, yeah, okay. So I think you guys are getting it. Yeah, so if you look at this polynomial, it factors as x plus 5, x minus 3. Okay. To get the plus 5 and the minus 3, you needed two numbers that multiply to be negative 15, but they need to add to be positive 2. Okay. So then x equals negative 5 and positive 3. Yeah, these are the places that are not in the domain. Okay. And yeah, so therefore, the domain you could say is everything to the left of negative 5, everything between negative 5 and positive 3, and everything after positive 3. All right, yeah, okay. If we look at the
question on
yes,
on this may be a silly question, but if why would the infinity not be part of the set? Like, why is it not included?
You mean why?
Like,
Are you asking why these two values are not in the domain, or are you
in the
asking?
interval notation, like square brackets says that it's included, right?
Yes, if you use square brackets, you'd be including that endpoint.
So why would infinity not be included?
Oh, okay. Yeah, so we don't include the two infinities because we don't consider them as part of the real line. So it would be, I guess, like improper to include them because they're kind of actually not there. So that, yeah,
Because like
you can't
infinity
really
isn't,
include, yeah,
yeah, and
it's
infinity isn't like a set number. It's just
essentially yes. So we don't want to include something that like doesn't actually exist, if you will. So that's why we just leave it out.
Okay.
If you study mathematics at a higher level, you do see people talk about things like this, but that's not something that you guys have to worry about in calculus, though. Okay.
Thank you.
Yeah. Okay. So yeah, so I'll talk about the horizontal asymptotes more when we get to it in this example. And then my colleague has also kind of addressed that, I believe, but I guess for horizontal asymptotes, ultimately you take a limit as x is approaching plus or minus infinity. But as I'm not going to get into limits just yet, so to actually see that, you'll have to, I guess, to check back in a couple of days, right? All right. But yeah, so at least for this problem, we'll talk about the horizontal asymptote, and then like why this function has a horizontal asymptote where it does. But let's look at the vertical asymptotes next, though. So for this function, who can maybe tell me where the vertical asymptotes would be? All right, so we've got a couple answers there. So let's take a look at it. So vertical asymptotes, we want to check where the denominator is 0. And we already did that for the domain. Okay, yeah, all right. But to distinguish between a vertical asymptote and a hole, if we take a look at the numerator of this problem, notice that we can also factor the numerator a little bit. In particular, if we factor 2 out from the 2 terms in the numerator. Okay, yeah, okay. So that x plus 5 kind of cancels out, if you will. And so we could simplify the function to be just 2 over x minus 3 whenever x is not equal to negative 5. So when x is not equal to negative 5, you can make that cancellation. Okay. So because of that, we actually don't have a vertical asymptote when x is negative 5, but we do still end up having one when x is equal to 3 then, okay? All right. So then instead of a vertical asymptote at x equals negative 5, we end up having a hole there instead. And so we have a hole instead of a vertical asymptote because of the sort of cancellation that was going on in the numerator and denominator.
So when there's a cancellation, that means it's going to be a hole.
Yes.
Everything makes sense now.
All right.
I think someone asked this too, but so does the hole is basically the discontinuity, right?
Yes. So a hole is a discontinuity. I actually haven't formally defined continuity yet. That's more of a calculus topic, though. So my colleague, I think, would probably cover it if he has the time to get to that point. Okay. Yeah. Okay. And then also maybe on the topic of discontinuities, I think people might, if you talk to like different professors, I think some of them actually have some like subtlety as to what they consider a discontinuity or not. I would say in your calculus class, you would consider a hole to be a discontinuity. But if you talk to some of your professors, you might be surprised to hear that they actually don't consider a hole to be a discontinuity. So that's maybe something you could talk to a professor about if they ever reveal that opinion, if you will, to you. All right. But yeah, in your calculus courses, though, you can consider a hole to be a discontinuity, though, for sure. Yeah. This function here, it does have a horizontal asymptote. Okay, all right. So let's talk about the horizontal asymptote for this problem. So it is the case that the numerator has a higher power. There would not be a horizontal asymptote. That is correct. So this one does not have a slant asymptote, but let's take a look at the horizontal asymptote. So the idea of the horizontal asymptote is you want to think about what was happening to your function when x is like a really when x is really far away from 0. Okay. So let's imagine like if x is kind of approaching positive infinity. So if it's like a really large positive number, what does our function look like when x is a really large number? Okay. Yeah, okay. So when x is really large in the numerator, that 10 is going to be pretty insignificant next to the 2x. So it's kind of like you just have 2x in the numerator. And likewise in the denominator, the x squared kind of overpowers or sort of dominates everything else. So when x is really large, you can almost pretend as if it's just x squared in the denominator. So your function behaves like the function 2 over x when x is large. And then here you can think about it when x is large, what's happening. The larger the x gets, the closer this gets to 0. So it's that idea that your function is approaching 0 as x is approaching infinity. That kind of indicates that you're going to have a horizontal asymptote at y equals 0. Okay.
Okay, so I'm a little confused on this little concept right here of like
Mm-hmm.
when the number gets larger and
Mm-hmm.
then somehow end up with the horizontal asymptote of 0. Can you just kind of explain to me how this works? Because it's kind of a little bit hard to grasp right now. It could become just
Right. Mm-hmm.
overthinking it. Or...
No, sure. Yeah, not a problem. So this kind of logic of it's not like this type of thinking. It's not like something that you usually do in your pre-cal classes. But it's something that you'll kind of be doing more of in your calculus courses. So I guess I want to sort of warm you guys up to it. So here, maybe think about what's happening if you plug in like a really large numbers for x. So I'll just maybe do maybe like one example right now. So let's say when x is 1,000. If you think about what's happening to the function if you try to plug in 1,000 for x. Okay. So you could actually kind of calculate this and you would find that it gets you a number that's pretty close to 0. But rather than getting the exact number, I've been doing a sort of like rough, sort of like
Like
conceptualizing
a
of what's
rough
going on
estimate.
instead. Yeah.
Okay. This makes a lot more sense now. Okay.
Yeah, so like in the numerator, you got 2,000 and then you're adding 10 to it. So I'm kind of thinking like, well, that 10, if you add it to 2,000, doesn't make a big difference.
Oh, okay. So like whenever
Mm-hmm.
the number gets like crazy, like super crazy, high, it just doesn't really matter at that point because it's just gonna become like extremely close to 0.
Right. Mm-hmm.
Okay,
That's
that
kind of
makes a
the
lot more
idea.
sense
Yeah.
now. All right. Thank
All
you.
right.
Thank you.
Yeah, no problem. Okay. So yeah, it's here just kind of the idea then that as x gets larger and larger, you find that your function gets closer and closer to 0 is what's going to happen. And so that's kind of the idea of a horizontal asymptote, which is that your function gets closer and closer to that value as x goes further and further out. So
I
mm-hmm.
vaguely remember this from one of my classes where there were 3 states and like
Mm-hmm.
this type of question could be. This one specifically like referenced when the denominator was greater than the numerator.
Mm-hmm.
It's just that I don't remember like exactly what the answer would be when the numerator is greater than the denominator and when both the numerator and denominator are equal. What would like the answer be
Okay.
at that case?
Yeah, I see. That's a good question. So yeah. So in all the examples I've done so far, I've been looking specifically at rational functions, okay? So for these rational functions, oh, thank you. For these rational functions, you can base the horizontal asymptote off the degrees of the numerator and denominator. So this problem, essentially what it boils down to for this problem is that your denominator does have a higher power than the numerator. Maybe higher degree than the numerator. So when the denominator has a higher degree for the rational functions, that leads to a horizontal asymptote of y equals 0. And it's kind of you can apply sort of a similar logic to what we talked about with the specific example to see why that would be the case whenever the denominator has a higher degree. So that's one of the three scenarios that you were asking about just now. The denominator has a higher degree than the numerator, you would get a horizontal asymptote of y equals 0 specifically. We've seen an example where the degrees were the same. But here, let me kind of make up another one on the spot right now. So in the case where the degrees of both the numerator and the denominator are the same, here I've kind of been using this sort of intuition that only the highest powers end up mattering in the end. When you're thinking about like as x goes out to infinity or minus infinity. So if I just focus on the highest power terms in the numerator and denominator, what happens is if they have the same degree, the powers of x would actually cancel out. And that kind of gives you this intuition that your function has this horizontal asymptote then. So I guess the value or the equation of the horizontal asymptote, you can think of it as like the ratio of the coefficients of the highest powers whenever they have the same degree, okay? That's kind of the second scenario that you were remembering. The third scenario was then if the numerator has a higher degree.
And so if the coefficients were both 1, then it would just be 1.
That's correct, yes.
Okay.
Are you like are you setting degree as in the exponent power, right? Not the coefficient.
I can't hear you too well. You might be too far away from your computer.
Oh, sorry. You mean by degree as in how many exponent powers there are, right? Not the coefficient.
Oh yeah, so the degree of a polynomial is the it's the highest power of x that you see essentially. So like here, in this example here, the numerator has degree 3 then, whereas the denominator has degree 2. Okay.
Yeah, that's right.
Okay. All right. Good. So when you're thinking about horizontal asymptotes, so again, you're kind of thinking about what's happening when x is a large number. When x is large or far away from 0, the intuition is that the highest powers of x kind of dominate, if you will. But in this case, your function, so if you kind of look at just the highest powers of x and you kind of simplify, you don't get a specific value. And so because you don't get a specific value, that kind of indicates your function has no horizontal asymptote, since it doesn't seem to be approaching any single value, okay? So this is the third scenario that someone was wondering about earlier. If the numerator has a higher degree, you would not have a horizontal asymptote is what's going to happen. I do not know what the acronym stands for, so someone will have to respond to that. Okay, but so that's kind of all I wanted to do with rational functions for today. I'm going to do a couple more examples. Sure, okay. Let me try to do an example involving a square root. Figure on bottom. Oh, okay, yeah, nice. All right. Yeah, okay. Yeah, okay, all right. Let's see here. So I think I'm going to look at just one example involving a square root right now, because we haven't done any of those yet. Okay, all right. So I have this new function which has a square root involved, which is something new. And for this problem, I just want to think about what would the domain of this function be. Okay, so someone kind of gave an answer. It wasn't quite right, but they were kind of on the right track. So whenever your function has a square root in it, and you're thinking about its domain, what you have to keep in mind is that you can only take the square root of a non-negative number, right? Okay. Yeah, so numbers under the square root can't be negative. If that's the case, we will consider it to be undefined, at least in our calculus courses here. Okay, so that means for this function to be defined, oops. So for this to be defined, the expression under the square root could not be negative. So this function is only defined whenever this expression under the square root is non-negative, okay? Okay, all right, okay. So right now, it would be correct to say that the domain of f is all x such that x to the fourth plus 5x cubed minus 24x squared is greater than or equal to 0. So this would be a true statement. domain is just all x that will satisfy that inequality. Okay. But that's maybe not a super like descriptive answer though, because if I just like throw out some values of x, like let's say if x is equal to 3 right now, could anyone tell me immediately at least whether x equals 3 would satisfy this inequality? So you could check it by plugging it into a calculator and crunching the numbers, but I guess ideally we'd like to have an answer that we could sort of easily tell exactly what values of x are in the domain and which are not. Okay. So whereas this is a correct statement, but we want to do better than this though, okay?
This is just a general like math question.
Yeah.
Why say non-negative? Is it to include like complex numbers, like imaginary numbers?
Okay, yeah, so when the expression under the square root is negative, that's when you get the complex numbers, right?
Okay.
With like the imaginary unit and all that. So in your calculus courses, you don't ever consider complex numbers though.
Okay. So
that means,
but is that why you say non-negative instead of positive?
so non-negative is slightly different from positive. So positive numbers would not include 0 basically.
Okay.
So when I say non-negative, that's going to be positive numbers and also including 0 as well.
Okay. Gotcha.
So yeah, having 0 under a square root is okay. It would just simplify to be 0. So because having 0 under the square root is okay, I want to include that possibility of the under the square root being equal to 0 for the domain. Okay?
Okay. Understood.
Okay, all right. Good question. Yeah, it's a subtle issue. I try not to do this, but sometimes when I'm really lazy, I will use the words positive and non-negative interchangeably, but that's very bad and you shouldn't do that. So it's a little bit hypocritical of me to say that, but
Okay. Yeah.
okay, all right. Yeah, so for this example, I wanted to try to give like a better answer aside from the answer that we have here right now. It's a correct statement, but it's not the most descriptive statement. So like we might like to give an answer in interval notation as someone has done in the chat. We can maybe try to verify if their answer was correct or not, because I'm not too sure right now. So I wanted to introduce kind of how to solve an inequality like this that we have here. And maybe does anyone have any ideas like how to solve that type of inequality for x? Okay, let's start by factoring it, okay? So yeah, that's, oh, crap. Okay, yeah, so that's what we're gonna start with first. Okay, looks like a couple of people got the right answer, maybe. We'll see. Yeah, but let's start by factoring this expression right now. So to factor it, the first thing we could do is we can actually factor out an x squared from all three of these terms. So let's start with that. Okay. And then x squared plus 5x minus 24. If we try to factor that polynomial, okay, yeah, so it factors as x plus 8, x minus 3. Okay. So they multiply to be negative 24. They add to be positive 5. Okay. Good. So then it looks like that's where everyone's been getting the numbers negative 8 and 3 for some of the answers that I see in the chat. Now, these are places where the function is, or where this expression is equal to 0. Okay. But I want to find not only where is it equal to 0, but I also want to find where is it going to be positive as well, because I want both greater than or equal to 0. Okay. So to figure out when is this expression going to be positive, there's sort of a device that we use, or like a technique that we use, which is to create like a sign chart. That's what I'm going to call it. Okay. So let me try to explain how this sign chart works. I'm not sure how many of you have seen this before, but this is something that you'll be doing a decent amount of in your first calculus class. So I wanted to just sort of introduce the idea in an example. So I'm just going to draw like a sort of number line right now. I'm going to mark these 3 points that we found just now from factoring. Okay. So at these 3 points, we know that this polynomial is going to be equal to 0. Okay. What I want to do is I want to figure out where is my polynomial going to be positive though. So to do that, we're going to take some test points. So I'm going to take a point in each of these intervals that this number line has been divided into. So if we imagine taking a number to the left of -8, any number would do. I'm just going to pick one at random. I'll pick -10. I'm also going to take a test point between -8 and 0. So maybe like -1 would work. I'm going to pick a test point between 0 and 3, so maybe +1. And I'm also going to take a test point to the right of 3, so a number like maybe 5. Okay. Okay. So I picked a test point in each of the intervals that we see there. And I'm going to plug each of those test points into my polynomial here. Okay. Oh, okay. And here, I'm going to write out the factored form of my polynomial. That's going to be easier to work with than the original. Okay. So if we plug in x equals -10, okay. Here I want to observe whether the polynomial is positive or negative. Okay. So the exact number isn't too important. If I plug in -10, okay, so here, when you square it, it's going to become positive, right? So that first factor, I guess it'll always turn out positive since it's being squared. Now, if we plug -10 into here, -10 plus 8 is -2. -10 minus 3 is also negative. So it's a double negative, so the final result is going to be positive in the end. So here I see that the polynomial should be positive in that interval. Okay. And if we plug in the other test points, let's plug in -1 next. So if we plug -1 in for x, this will be positive. This will be positive. This would be negative though, if we plug in -1 for x. So altogether, that results in a negative number. So the polynomial appears to be negative in that interval from -8 to 0. Okay, all right. Let's plug in the test point +1. So if I plug in 1 for x, positive, positive, negative, so it's going to be negative again there. And if I plug in 5 for x into each of these 3 expressions, everything's going to be positive. So it's all greater than 0. So it's going to be positive overall. Okay. All right, yeah, so it looks like people have kind of figured out what the answer is going to be. Okay. So the domain is the values of x that will satisfy this inequality. And based off our sign chart, we see that this polynomial appears to be positive from minus infinity to minus 8. Here I put a bracket around the negative 8 this time. So the reason why I'm putting a negative 8 there is because at negative 8, the polynomial is equal to 0. And so that is part of the domain because it just needs to be greater than or equal to 0. So we do want to include the places where it was equal to 0 in the domain, and that's why we want to use a bracket there. Okay. Now it's negative between minus 8 and 0, and that would make our function undefined. So the interval minus 8 to 0 should not be in the domain. When x is equal to 0, the inside of the square root becomes 0, and that does work. That is defined. So I'd want to include 0 in the domain. I think I saw someone do this. I think. Okay, so that's not quite right. I think you could do 2 things for that, though. So you could include a closed interval from 0 to 0, and that technically that would work there. But another possibility, if it's just a single number, what people might also do is use a curly brace if it's a single number like that. Okay. So at least to me, either of these 2 would be acceptable to indicate that x equals 0 should be in the domain. Uh, 0 to 3 is no good though, because the inside of the square root will be negative, so it'll be undefined there. But starting at 3 and going out to infinity becomes greater than or equal to 0 again. So we want to include this in the domain as well. Okay. To have just a 0 without using brackets, so I would say yes. That would probably be counted as incorrect. Now it's possible that you have a somewhat lenient grader, so they might be like, well, I understand what they're saying, and they might give you credit or something like that. I guess from a sort of purely like technical level, that would be incorrect. So unless you had like a lenient grader, it would probably be counted as wrong, I would say, if that were the case. Okay. Yeah. So. Yeah, so we did include 0 because at x equals 0, the inside of the square root becomes 0, but that is actually okay for square roots. So that's why we want to make sure it is included rather than excluded. So maybe if we sort of contrast with the other examples that we saw earlier, the other examples didn't involve square roots, but they involved like the denominators, right? And denominators can't be 0, so we had to like always exclude the points where it's 0. For a square root, it's okay to have a 0 under the square root though. So that's why we want to include those points. Okay, yeah, so that would not work because like from -8 to 0, the inside of the square root was negative. So that wouldn't be part of the domain, okay? Okay, yeah. So yeah, for this part down here, what I was doing was I was plugging in the various test points that I picked from like each of these intervals. I was plugging it into our polynomial here to see if the result was positive or negative is what I was doing. So then just like for instance, when we plug -10 into here, so like -10, when you square it, it becomes positive. So I just note that it's positive. -10, if we plug it into the second term here, -10 plus 8 is negative. So I indicate that's negative. And then finally, I plug -10 into the last one, and -10 minus 3 is also negative, okay? So what happens is you have a positive times a negative times a negative. So like ultimately the result is positive, okay? And then the other ones are similar as well, just using the other values of x that we plugged in. Yeah, so again, 0 is included because the function is defined when the inside of the square root is 0. Yeah, this session is being recorded, so we will post the recording to our YouTube channel, and we will share it with everyone once we have it up, okay? Yeah, so then for the square root function, since it is okay to have 0 under the square root, so for functions like this, the domain is wherever the inside is greater than or equal to 0, okay? And essentially because we're including the possibility of being equal to 0, since that is defined when you have a 0 under the square root, there's nothing, this is perfectly good. Okay. So yeah, so for something like this, the domain you look for where the under the square root expression is then or equal to 0. Okay. All right. Yeah, so with this example, I wanted to just kind of introduce like solving a sort of inequality with the sign chart. I'm not sure how much experience you guys have with that, but it's something that you guys will be doing a bit of in your calculus courses, at least in the first calculus course that you end up taking. So the first course in your sequence. So I at least wanted to kind of introduce it to you guys with an example. I've got about 25-ish minutes left. So I want to talk a little bit about some non-algebraic functions as well. In particular, I wanted to spend a little bit of time talking about exponential and logarithmic functions. So up until now, we've just been working with algebraic functions, which were essentially like powers of x. Yeah, that's fine. So that's what we're reviewing right now, right? I think last time we tried just going straight to calculus without a review. But yeah, now we're doing like a review first, and then we're doing a little bit of calculus at the end is what we're doing. So, okay. So any non-algebraic function is called a transcendental function. That terminology is maybe not too important, but I thought I would go ahead and introduce it to you guys. And some examples of transcendental functions, so functions which are not algebraic. So exponential functions and logarithmic functions, that's what I'm going to try to talk about for the rest of today. So an exponential function is something like e to the x. Instead of the number e, you could also have things like 2 to the x, 3 to the x, and so forth. If you guys aren't too familiar with it, e is a constant like the number pi. Pi is about 3.14. E is approximately 2.718, okay? And then there was related to the exponential functions, we had these logarithm functions, which I'll talk more about in a bit, but in your calculus courses, you'll be working almost exclusively with the natural log function in particular. So ln denotes natural log. That's kind of what it stands for. If you guys are kind of familiar with log functions, you've maybe seen like other things like log base 10, log base 2 before. The natural log function is specifically a logarithm with a base of e. Okay. So we almost always work with a base of e in the calculus courses. So for exponential functions, e to the x is kind of the most important one, and for the logarithm functions, the natural log is the most important one for us, at least in calculus. Other examples of transcendental functions are the trigonometric functions, but I will not be doing that today. I will be talking more about that tomorrow, though, so that's what Precal Day 2 is going to be about. All right, no problem, yeah. So I'll talk a little bit about exponential and logarithm functions. First, I just want to kind of give you guys a picture of the graph. So I'll start with the exponential e to the x. So its graph will look something like this. When x is equal to 0, e to the power of 0. Well, so any number to a power of 0 is considered 1, except for 0 to a power of 0, which is undefined. Well, maybe it depends on the context, but x to the 0, if you guys remember, an exponent of 0 just makes it equal to 1. Except kind of a special case when x equals 0. And 0 to a power of 0 is a little bit of a mystery. So let's not talk about that. All right. So yeah, notice that for graph of e to the x, it does have a horizontal asymptote at y equals 0. So that's kind of interesting to note, I suppose. And then it's also unbounded over here, so it just kind of blows up to infinity as x gets larger and larger, okay? Talking a little bit about the logarithms, specifically the natural log function. So if you guys don't remember, logarithm functions were defined to be like the inverse of the exponential functions. So the idea of, say, the natural log function in particular is, so let's say in my picture, I'm going to just mark a value over here on the positive y-axis. I'm just going to call it t right now. So when you look at the exponential graph, you can see that there is a value down here on the x-axis, yeah, such that if I take e and raise it to that power, it returns a value of t. Okay. So this sort of mystery number here on the x-axis, we call that number the natural log of t. Okay. So essentially, the natural log satisfies, or it's kind of like the solution to this equation. E to what power will give you this number t. That answer, that what number do you have to raise e to a power to? The answer is natural log of t, okay? So that's kind of the idea of the natural log function. If I were to draw a graph of the natural log function, looks something like this. Okay. It's maybe not super important to know this, but I think it's nice to know. So the graph of the natural log function happens to be just a reflection of the exponential graph along the diagonal. So any two functions which are inverses of each other, the graph has this property. Yeah, so that is correct. So I guess here I was specifically kind of looking at a base of e, but for any other like base b, like b to a power of log base b of t would equal to t, okay? So yeah, that works for any other base. All right. One of the, so I'm gonna talk about some of the properties of natural log, but before that, I wanna talk a little bit more about exponential. So one thing that's kind of good to know about the exponential function is that if you look at its graph, it's always above the x-axis, right? So one kind of useful observation to make is that e to a power, no matter what the exponent is, e to any power always ends up being positive. Okay. It never dips below the x-axis, so it's never negative. It never equals 0 either, so it never actually touches the x-axis anywhere, okay? So this is often good to know when you're solving equations involving the exponential. Yeah. Let's see here. I think what I want to go ahead and do, just to try to wrap up today, so I think I only have time for about one more topic. So I think the topic I want to get to then is properties of the logarithm functions. So I think I've everything else that I wanted to talk about, not that much, but I think the most important one is properties of logs. So that's what I'm going to jump to at this point. Okay. So here I want to talk about some of the properties of the logarithm functions in particular. I'm going to write all these properties using the natural log function, but these properties apply to a logarithm of any base, okay? So one of the properties of the logarithm function is it kind of turns multiplication into addition in the sense that natural log of a product, so natural log of a times b, is equal to natural log of a plus natural log of b. There's kind of a similar property that natural log turns a quotient into a difference. Another property of logarithm functions. So if you have a logarithm of something being raised to a power. Okay, so if I have natural log of, say, x to the power of k, I can take that power and move it out to the front as a coefficient. So natural log of x to the k, that's actually equivalent to k times the natural log of x. And then we saw earlier how like e to a power of natural log of x, the e and the natural log, they sort of cancel and just give you x. That's kind of like one way you can interpret the statement that we had over here. So it's kind of like the e and the natural log cancel each other out. It works the other way around, as that if you have like natural log of e to the x, when you put them together like that, the natural log and the e will also cancel each other out and just leave you with whatever was in the exponent of e. Okay, so these are some of the properties I wanted to mention. Again, these properties, they hold for a logarithm of any other base. These two properties down here would be written like this, for instance. Okay. And then likewise, if you just replace natural log with log of any other base, these same properties are going to hold as well. Okay. And I just want to do kind of one final example for today involving making use of these properties of logarithms that I just wrote down. So this will be the last example for today. So here I'm going to write down a fairly complicated expression. So let's do natural log of, I'm going to do maybe cube root of x plus 5. X squared plus 4 to the power 6. Maybe 10x ex squared minus 1. Okay. All right, so here I've written down a pretty complicated looking function. And what I want to do in this example is to just simplify this expression using the properties of natural log that we see over here, okay? Okay. So in order to do that, here are the first thing that we'll kind of note is we do have like natural log of a quotient. Yeah, so that suggests that I apply the second property right now. So instead of natural log of a quotient, we can convert that into a difference of natural log of the numerator. And then we can do minus natural log of the denominator. So that was using the second property over here. And then we want to maybe continue simplifying this some more. So what else do you guys see that I might be able to do? Yeah, so we can use the first property in a couple of places. So Anytime you have a product inside of a log, you can try to apply this first property. So here we've got natural log of a product. So we can think of the cube root as like a, this polynomial to a power of 6, it's like our b. So we can split that as natural log of a plus natural log of b. Okay, yeah, all right. Okay, all right. So yeah, so we'll do some of those things next, but right now let's continue applying this first property though, just to split these apart even more. I can apply the first property to this term as well. So now let's see here. This one, you want to be maybe a little bit careful. So we have a natural log here, and you can maybe look at it slightly different ways, but you might think of it as like having 3 things multiplying, 10 times x and times the exponential. Yeah, okay, yeah. So we're going to do that next, but right now, looking at this expression, if we apply the first property, we can convert this product into a sum. Oops. So we can split it as like natural log of 10 plus natural log of x plus natural log of e to the x squared minus 1. Now here, just to be a little bit careful though, so this logarithm expands as this according to the first property. So this minus sign that was in front of this natural log will continue to be in front of everything that we expanded it into then, okay? So you have a minus sign in front of all 3 of them, not just in front of the first one. So that's kind of a subtlety to be aware of. Okay. So then if we continue simplifying a bit more, so I know someone in the chat suggested that we rewrite this cube root. So cube root of x plus 5, you can rewrite that as x plus 5 to a power of 1/3. Okay. So just like how a square root is raising to a power of 1/2, a cube root is raising to a power of 1/3. And we can use the third property for something like this. So that third property allows us to take the exponent of 1/3 and pull it out to the front. Okay. All right, and then yeah, we're going to do the same with this term here. We can also use the third property and pull the 6 out to the front. Okay. Over here, if I distribute the minus into the brackets, we could do minus natural log of 10 minus natural log of x, and then minus, and then here we have natural log of e to a power. So for this term, we can use this property here that when you have natural log of e to a power, the natural log and the e, they sort of cancel each other out. They leave you with whatever was in the exponent. So here, when the L and the E cancel, we'd be left with x squared minus 1. And then that's being subtracted because of the minus when we distribute into the brackets, okay? And so at this point, this would be as simplified as we can make our function using those properties of logarithms that I had written over here, okay? So that's where I'm going to end my review for the day. Do you guys have any questions about anything? All right, so I'm gonna go ahead and just post the link in the chat right now. So this link is just for you guys to leave us some feedback on how the workshop went. All right, so I'm gonna post the link, and for those of you who want to leave us feedback, we'd appreciate it if you took just a couple minutes to fill it out. Yes.
One quick question would
Yep.
be, so earlier we found the domain of a function that was under a square root. What if we were finding
Yes.
the domain of a function that had parentheses with an exponent?
Okay.
Would that be because it was x is
Parentheses with
greater
an
than or equal to
exponent.
0 earlier?
So I guess it'll maybe depend. So so if you have like something in parentheses being raised to a power, it depends on what that power is going to be then. So because like raising to a power, say like 2 versus like a half versus like a third, just has some examples right now.
Right.
So I guess when you're squaring something, so there's no number that you can't square.
Okay.
So in that sense, when you're squaring something, it wouldn't really have an effect on the domain. So it would kind of just be based off whatever the domain of the inside was. That would be the domain of this function. Power 1/2 is the same as square root though.
Right.
So if you got a function in the parentheses like that, domain would be wherever that expression is, or wherever that function is greater than or equal to 0 then, okay?
Okay. So then with
Okay.
raised to the exponent of 1/3, it would be similar?
Well, let's think so. For cube roots, because this is what this would be.
Right.
So actually cube roots are okay. You can actually do a cube root of a negative number.
Oh, so the determinant is whether or not the negative number can be taken out, because that's undefined otherwise, right?
Right, yeah. So it's kind of maybe
Okay.
like if it's like an even root, you'd have
Okay.
to look at where the function is greater than or equal to 0. But yeah, for like an odd root, there's actually no issue with that though. So here,
Okay.
like domain of this kind of function would just be whatever the domain of f itself was then.
Okay.
Maybe I'll say one more thing, which is if I sort of combine the roots with a fraction, so if I did something like this, right? So here, although it's okay to have a 0 in the square root, but it's not okay to have a 0 in the denominator, right? So if I did something like this, you'd want to look for where the function was strictly positive.
Okay, so it
Because
has
it's
to
in
be
the
greater.
denominator, so yeah, there you have to remove 0 if it's in the denominator, yeah.
Okay. And then if you had, say, if you had something raised to the third power, then that would also not matter because it would be making something negative, and so you'd have to use the x is greater than or equal to 0 thing as well, right?
Yeah, that's right, yeah.
Okay, so it's just based on whether or not that negative can exist. Thank you.
Yep, yep. Let's see here. Where's my, oh, there it is. I had an example of this as well, although I didn't have the time to work it out, but just maybe like a note, which is kind of similar to square root. But when you look at a natural log, or just like any logarithm, I suppose, but I'll continue working with natural log. So one of the things to notice about the domain of natural log is it's only defined when x is positive. So if you have like natural log of some function, and you're asking what's the domain of this going to be, okay. So for natural log, the inside has to be strictly positive. So like here's where you'd have a strict inequality as well. Okay. So then just like a slight contrast with square roots, where it is okay to have 0 under a square root. So you would do like greater than or equal to 0 if you're looking for the domain of that. But yeah, natural log will be strictly positive though, because it's not defined when the inside is 0. Okay. So I had another example of that, but I didn't get around to it. Good question. So not tomorrow. So tomorrow I'm gonna just review the trig functions and trigonometry a little bit. We'll get into limits and like the actual calculus stuff starting on Wednesday. All right, no problem. Yeah, no problem. So we'll see you guys tomorrow as well.